So we are like 3 minutes in the show, and today I'm working on a dual power switch for fast transient load switching. I designed the buck converter using LM61440 about a month ago or a month and a half ago, and the prototype is manufactured and tested. I presented it on LinkedIn along with sharing two videos, because the entire design took 2 live streams. So I shared everything. Everything is accessible on my profile, on LinkedIn, on YouTube, basically everywhere from my point of view. And I was asked to share the load transient characteristics from 100 milliamps to 4 amps. So because in the data sheet there is only this characteristics, this waveform for load transient from 2 amps to 4 amps back to 2 amps. And I was asked to deliver the load transient characteristics from the lower current. So I measured the characteristics during my testing, but my switch is not ideal. It's too slow, and there is quite inductance in the PCB traces. Frankly, it's not PCB, it's a universal board with bottom layer soldering, so nothing nice to see, nothing nice to use. And I decided to design a better one with BNC at the inputs and with better MOSFETs, and yeah, to provide me with better switching characteristics. Yes, that's my intention. So the motivation is to measure something like this, but from the lower current value. I suppose there will be some tuning of the feedback network on the PC, on the buck converter. There is a feed-forward capacitor in the voltage divider, so we can compensate the feedback network, and yeah, many things basically can be changed on the PCB, like yeah, everything was recommended: the number of output capacitors, the type of output capacitors, the feedback voltage divider, as I said, the capacitor, the feedback divider to provide some compensation to the feedback for the error amplifier, etc., etc. But I need the the highest quality possible power switch. So I started in KiCad. There is a short checklist. I want the BNC inputs isolated with optocouplers, not strictly isolated. I will place a jumper on it to be able to connect the ground side of the BNC to the ground of the PCB. I want this switch to be pretty universal, not only for this kind of measurement, but I want it to be useful for other type of measurement, for some load testing. So let's continue with the following point of the checklist: gate drivers. Gate drivers will be used to provide a fast switching. If you are here since the beginning of the stream, you saw that I checked the capacitance of the most likely used MOSFET. The most likely used MOSFET is this Texas Instruments CSD 19534. I caused reloading of the data sheet, which was not intended. I'm sorry for the interruption. Yeah, there is a maximum input capacitance of this MOSFET. It means its capacitance between the gate and the source electrode of the transistor of the MOSFET. And we need to charge and recharge this capacity as fast as possible. Plus, I want to use 2 MOSFETs in parallel. So it means there will be more than 3 nanofarads of input capacitance. And I checked the capability of these MOSFET drivers I want to use, and they say that 1 nanofarad can be recharged in 18 nanoseconds. Then I checked the transient waveform of the buck converter in the data sheet, and they measured that the rise time and fall time of the current step characteristics was 2 microseconds. So it means that 2 microseconds is something like the minimal time that we can consider. And back to the gate driver, you can see that we are talking about tenths of nanoseconds. So we are two orders of magnitude below the considered time. So we will be good to go with the MOSFET driver like this, MCP 1415 or 1416. Frankly, I don't know what's the reason, what's the difference between these two. I think I already checked already used the 16, which is, yeah, there are 4 versions. 15 has the negative output. It means it can be used for PMOSes, I don't know, but I will use the 16 with the normal pinout, not the like reversed or the modified pinout. I'm checking the usage of the negative output driver. Yeah, probably for the driving the following gate driver or gate driving circuit, I don't know, because the limiting value, the limiting voltage on the output is where it is, absolute maximum is 20, but on output there is, where is the limiting maximum voltage? I can't see it, but definitely not more than the power supply voltage. And I want to not be limited by the voltage of the gate driver. Anyway, we have first comment. Hi, LinkedIn user. How are you? Thank you for watching. Thank you for being here. So, 2 parallel MOSFETs with the ability to connect a jumper or switch between source and gate to like short circuit the switch. Drain protection diodes. Yeah, I will use these. Where are you? Here. These power DI Schottky diodes, as I prepared before. Light load terminals. Yeah, light load MOSFET. This is the heavy load light load MOSFET, I will load terminals, yes. Input LEDs. I already placed LED to the input section. Output LEDs, okay. I will use the this drain will sink the current of the output LED as well. We will see in a while. Terminal and mounting hole output. Yes, I want to use the terminals as well as the mounting holes to be able to connect directly the hooks, the cable hooks. And I'm thinking out loud that besides of the PNC, I want to place the terminal as well, because sometimes it's useful to be able to connect not only the BNC cable, but as well universal wires, universal cable. So this will be the input section. Here is something I don't know I need. I think I can omit this. Let's check what it is. This is a snippet of a circuit I used before. This is like digital output. Yeah, digital output. Yeah, that can be used like a formal, like a signal forming device. But I think, yeah. I have to keep in mind that the rising and falling edges must be as steep as possible, because the slow, steep edges would influence the measurement. So this is not wanted. This is why I previously used this driver, this digital optocoupler, because the driving capability of this optocoupler is quite high. Yeah, and this low-cost optocoupler is not. I don't know if it's fast enough or not. Yeah, definitely in the range of microseconds. Definitely yes, but there can be like some transition characteristics between input and output that can make the edges not so steep. Is it something in the data sheet? We need some time characteristics. Load response time. Load resistance is quite high. Yeah, and we are in the time. Yeah. Definitely, I will use the following digital output optocoupler because of its characteristics and driving capability. Yeah, and definitely I want to be able to measure the signal here as well, because this is my signal. The switching edge here from the generator will be, or this edge will be delayed from this edge. Here is a delay, here is the delay. There are some capacities, there are some transition times needed, propagation delay. So this should be accessible as well for measurement. And here I want to use double MOSFET here. like this. Here will be the freewheeling diode protecting the drain of the MOSFETs for inductive loads. And here will be the terminal, output terminal. With two mounting holes as solder joints. I want to use this. No. These mounting holes and place them as close as possible to the PCB edge to be able to use the cable hooks, not only the terminal connection. So something like this. Here will be the external voltage up to 100 volts. This MOSFET is 100 volt N-channel MOSFET. This diode is 100 volt Schottky diode. And as I said, we need like optical check of the output. So when the MOSFET is switched, and I have to place the serial diode here. I think 41, 48 is 75 volts. It's not enough. We need at least 100 volt diode. So let's check my inventory, not inventory database. We need 100 volt. It doesn't have to be Schottky. Yeah, previously or recently I used this one. This is 123 that can be used. And we need to place the diode here. Why? Because if you imagine here, let's check the forward voltages or the reverse voltage is 250. If you imagine 100 volt here, the MOSFET is not conductive, but without this diode, the 100 volt against 5 volt, and the only barrier is the LED. And the maximal voltage of this LED, let me check the data sheet, is definitely not high enough. Reverse voltage is 5 volt. You can see at least at max 12 volts for blue ones. So we need to place the protection diode here to create some barrier against like damaging this LED. Other option would be to use like auxiliary switch, auxiliary MOSFET with like for switching the LED. But if we want to monitor the output, this wouldn't be very useful because we would use another switch. And if one of these MOSFETs is like broken or short circuit, and we would use the auxiliary N-channel MOSFET for switching the LED would be off, but the switch would be constantly on if short circuited. So we need something like this. So let's get back to the checklist, and I will start checking it. So BNC input is there, gate driver is there, 10 volt power input is there, 5 volt LDO is there. Above the schematic I will show you in a while. 100 parallel CSD MOSFET with SD jumper, not yet. So let's get back to it. Yeah, as I said, we want to be able to short circuit this section and not only using a jumper, but using the switch. And a switch can be connected, yeah, for instance, on the that can work on the electrodes of this header. But I'm thinking that if the current is not, yeah, it will work. It will work. My intention is to be in the band of up to, I don't know, 5 amp. So one jumper section would be enough. But yeah, I'm thinking out loud. I will use the dual header. So in that case, I can place 2 jumpers, or jumper and a switch at the same time, or yeah, I don't know. This will be the optimal solution. So get back to the checklist. So we have 100 volt MOSFET with SD jumper and a switch contacts. Yes, we have. Drain protection diodes we have. Light load terminals we don't have. Light load MOSFETs we don't have. Heavy load terminals we have. We have a terminal with 2 mounting holes. Input LEDs we have. Output LED we have. Terminal and mounting hole output. Yes, it means that there must be terminal and mounting holes, and we have it, or them. So here is the LDO, as I mentioned. This is the external power supply entry with a terminal and mounting holes, and there is a very simple LDO with 5 volt output. But yeah, this LDO is not enough. Why? Because that gate driver can deliver peak current of 1.5, I think, yeah, amp. We will have, in fact, 2 gate drivers for heavy load and light load. So the peak current of this gate driver can be up to 1.5 amp. Yes. Note 1 says that tested during, okay, not production tested, not a problem, but this LDO is pretty simple, easy to use, but the maximum current is only 500 milliamps, and I don't know what is the maximal peak current. We can help us using battery of capacitors to the output of the LDO to cover the peak currents, because the peak currents will be very short. As we checked, the transition takes like tens of nanoseconds. So I think we can be good to go, but I have to check it. Output current is minimal 800, maximal 1030. Ideally, I would we have to find the 5 volt version. 2.5, 3.3, 5 volt, yeah, the same. Yeah, I will place there a battery of capacitors to cover the very narrow current peaks, and I will stick with this LDO. So let's say that I will use a few of these, but let's get back to the datasheet of the LDO. We have to check what is the maximal output capacitance, which is another limiting value. Not yeah, there isn't specified the maximum capacitance of the on the output. Yeah, I have to check here is 100 microfarads, so this looks okay. But I am interested in the transient transfer characteristics. Transfer, no, nothing like this in this datasheet. Electrical characteristics. Yeah, we will stick with the okay. I will use a few low ESR about 5 ESR capacitors, and we will see how it works. Other option would be to use the buck converter for high current switching capabilities, which is not a bad idea. Yeah. We can use the LMR as I used before. Let me check. Yeah, LMR 5420 is 2 amp. LMR 5420. Or TPS 5430. That's 3 amp with industrial input voltage range. That looks good. Yeah. Let's see its data sheet, what they say about transient characteristics. So here is the data sheet of the considered of the back I might use. 500 kilohertz. So let's find the transient response. Yeah, nothing crazy fast, as you can see. Yeah, that's a question. What's faster, the LDO with the capacitor battery, or low frequency or mid frequency range buck converter? According to this, when you can see that the time divided, the time scale is 200 microseconds, and it means that this edge is I don't know, maybe 20 microseconds, and the transient response on voltage is not very great. Yeah, we are speaking about 30 millivolts, something like this. But you know what? I will keep this simple. I will use the LDO as I already placed with the battery of capacitors, and for a future measurement or possible measurement, I will place a test point here at the output of the LDO. Definitely I will place a similar test point. Yeah, I can place the header with one. Yeah, for instance, this with one pin only. So I can monitor, you know what? I will place two of them here. So I can measure the voltage here, and if I see that there is a like unhealthy waveform on the 5 voltage output, I can make some adjustments. Okay, so yeah, the last point is checked, and so here can be the like heavy load switch, and I need another channel for light load switching, but it will be simpler because I will use only a single MOSFET. The other parts will stay the same. So we have two channels with the BNC input or the pin header input. We have, let me close some windows here to see your comments. There is no any. There are no any. there isn't any new comment. I'm sorry for my lingo. I'll get back to schematics. We have the BNC at the input. We have the possibility to connect the signal on the two pin header. There is a protection diode for the optocoupler LED. There is possibility to connect the ground side of the BNC with the ground of the system. There is the monitoring LED of the state. There is a digital output optocoupler driving the input of the input of the gate driver. The gate driver driving two MOSFETs in parallel. We can place a gate resistor in here, but I want to place 0805 resistor, but I can see that I can't see 10 ohm resistor, so it will be a component placer, so I will place 15. You know what? I will place 0 ohm resistor, and then I can play with other values during my testing. Right now, this is a component placer only, and we can decide about the value later. So, 2 MOSFETs, monitoring LED, monitoring the state of the output. This is the power entry for the switching voltage. So here will be connected, here will be the load like this. I think I'm missing something. Let me check. Here will be the virtual load. Just a picture like this. But we need to connect the we need to connect the output voltage, the voltage of the measuring voltage of the measuring power supply. So we need another terminal, another. So this is the load and the terminal connecting the power supply will be here. Here and here. Sorry for my drawing. Skills. Something like this. So here will be connected like 100. For instance, I will place the label here. 100 volt, for instance, connecting here, and the other side will be ground. Here will be our load, and this is our load switch. So the external power supply supplying the load and switching by the MOSFET, and here is our return path. Okay, that's correct. That's correct, and because this is the light load switch, which can, or not can, which shares the external voltage, I can use this. Okay, so here are our terminals with mounting holes. Here will be our load connected to the terminal. This is heavy load. This is light load. Okay, and we need 4 mounting holes for the PCB. I will use the mounting holes with pads, 4 of them, in the corner of the PCB. Yes. So let's check the checklist. Light load terminals we have, light load MOSFET we have. Okay, so this can be our simple fast transient load switch. Yeah, I can't see any issue right now. Input, LED, octocoupler for the gate driver, ground is connected, so there is no isolation function, there is only driving capability of its output. Basically, there can be the Schmidt buffer or something like this. But yeah, that can be the case. Let me check. We want. Yeah, what's the important point? What's the logic? Here is when the output is active, high, this will be low, and the LED is connected from like supplied from the 5 volt, so low level will cause the activity, and output is direct, not negated, so there is no polarity inversion. So we need either buffer or inverter. So I think I have single Schmidt trigger inverter here, single package, single gate package. Here is the inverter as well, single gate. Here is the buffer gate, single package. So let's check the price availability, because this Schmidt trigger is definitely an alternative to the digital output optocoupler, because we need another isolation, and driving capability of this Schmidt trigger is not so important because we drive only the gate driver. Okay, and switching characteristics, okay, nanoseconds, okay, and the driving capability. This is output characteristics. Yeah, they are talking about 32 milliamps, so this is the normal CMOS driver, LVC logic. Okay, so yeah, 24 milliamps output drive for 3.3. Yeah, let's get back here. One unit is 36 cents, US dollar cents, and the price of the, yeah, let me place it here for possible usage. And here is this digital output optocoupler, and the price is 3 times higher. Output current is 50 milliamps, which is not needed. Here we are driving the gate driver only. The voltage range is up to 30, but we drive it from 5 volts, and the LVC accept 5.5. I think the maximum allowed 6.5 is absolute maximum, and typical is 5.5. Okay, so okay, I guess I will change this point, this octocoupler, and I will replace it with the Schmidt buffer, because it makes more sense to me. What do you think? Is there somebody here listening to us or not? So I'm making a space for this. Yes, but back to the signal logic. Here is the negation, and when there is only a buffer, this will be negated. So we need inverter, not buffer. So we need not 1G17, but we need 1G14, which is our inverter. This is the same package, but the AHC logic, I can see that I have 14 in LVC as well, but this is too small package. I think it's too small, and I'm not interested in creating new symbol just for this. So let's check the size of the SOT553. Open. Yeah, 1.6, 1.6, and we have a CT 2 times 2. Yeah, I would like to use the 2 times 2 rather. Yeah, I will use the AHC inverter. Yes. This is the coupling capacitor of for the IC. Yes, something like this. And I will do the same here. So you know what? I will copy the entire block when it's complete. Like this. You know what? When I say entire block, I will copy the entire block. Yes, so we have our inverter, supplied from 5 volts. There is the output monitoring connector. Yes, just one isolation here. That makes more sense. I think that's better, much better. Yeah, let me make a very short break, I have to visit a room, and yeah, you know what it is. This is my favorite KiCad tutorial. I'm back here in a minute. I'm back. So KiCad for Makers is my new online tutorial, online course, where you can design for very reasonable price this PCB. Here is a 𝗲𝗶𝗃 2-core MCU. There is M2 connector for blue node cards, 2 power supplies, 4 power digital outputs, 4 analog inputs, 2 USB Type-C connectors, SIM card slot, a few LEDs, Arduino compatible board. Yeah, everything what you need for your project, and you will learn many things when following my steps or just watching the tutorial. So highly recommend it. Let's get back to the design. Yeah, I think we are good to go. We have power supply, simplified input stage with gate drivers, MOSFETs, LED monitoring the output of the MOSFETs, terminals connecting the external power supply plus the loads. Pin headers able to connect the switch, the rocket switches, or rock switches, or the jumper, freewheeling diodes, 2 grounds. Yeah. Let's annotate the schematic as is, and let's see the ERC. Many findings. Let's start with errors. Yeah, we have to add some power flags. What's this? Doesn't match copy in library power. Okay. So let's change the symbols, all of them. Ground needs to be connected with power as well. All ground symbols doesn't match copy of my database. I can't understand. We have 2 possibilities: to update all the symbols or change them. So let's see if it helps. Yeah, it helped. So ground needs, you know what, I will update all symbols to avoid these stupid mistakes or findings. So here is power flag for ground, VCC as well. Okay. Yeah. Pin not connected. Oh, sure. Zero errors, zero warnings. Okay. So, I have a few more minutes, let's say 15 or maybe 20. So let's update the PCB. Let's start the component placement. So, as usual, I will draw. This time, my intention is to design about 80 to 80 millimeter PCB. So I will start with the square of this size, 80 to 80, and we will see then. Why? Because there are 3 power MOSFETs and I want to dedicate a reasonable and significant area on the PCB as a heatsink heatsink for these MOSFETs. So this is why I need a rather big PCB for this. Plus, I want stability of on the table. This will be a measuring tool. So I want the stability on the desk, and the large area, the larger size of the PCB will help. Board finish, not important, but just for renders. Yeah, for layer, definitely. Constraints I can keep, and the predefined, I think, will be as usual. Plus, yeah, probably I will use only 0.5 millimeters or 1 millimeter track width, and larger track width will be used as polygons. Okay, so let's update the PCB to see what's the situation here. We have 8 warnings. No net found for J9 PAT 4, PAT 9, PAT 4 and PAT 3, and this is 4 times repeated. So let's check the J9. What is J9? J9 is BNC. Okay, this means that there is an issue with the footprint. There are mounting holes 3 and 4. Let's check the data sheet. Mounting holes only 2 millimeter hole, and this is solderable or not, I am not sure now. Yes. So we need to modify the symbol. I don't know why my symbol doesn't contain these 2 pads. It's a historical symbol that has its own issues, as we all have. Like this. Okay, let's update the PCB. There shouldn't be any. Yes, all warnings were solved. So, disabling or making invisible for the values. Select screen we don't need. You know what? This footprint of the BNC, which was like one of the oldest footprints of my database, is a big. It doesn't contain the fabrication layer. And I have to check. Yeah, you can see that the silk screen is over the pads. Not my best work, I can say. Not my best work. Okay, that's not bad. The silk screen matches the shape pretty good. Okay, but not. I want the edge of the silk screen at the edge of the package, because then it will mark the edge of the PCB. So we need something like this. Yes, that can work. Okay. Okay, that's good. So now I have to update these footprints, all of them. Yes, much better. Much better. No, that's not much better. That's only slightly better, because there is missing the reference string. Yeah, I clearly remember I worked on this footprint as well as on this one long time ago, and we all learn. Okay, let's start as usual with the mounting hole in the top left corner. Yeah, I'm using the newest KiCad 9.0.5, which has some new set of bugs, but what they corrected, and as they, I mean the developers, software developers, they corrected the placement on the grid. That's good, but as I said, there's some new bugs. There are some new bugs, so I'm looking forward for the following version, or just some bug fixing version, I don't know. Okay, so I want to move this like here, and as usual, I will use the split screen mode, and we will separate the footprints into blocks. Here is the block with the LDO. Here is the block of the heavy load switch. And here is the light load switch block, like this. Okay. And what will be our the basic component placement? We want the input PNCs to be on one edge, on a common edge for these two PNCs. For instance, I'm designing this PCB for me, for myself. So my functional generator is on my right side. So the input PNCs will be on the right side. Just about here. The load terminals, all of them, it means this, 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 and no, not these ones, not these ones, this, and these three components will be on the opposite edge, here. The external power supply, the measured power supply, like the power supply being measured, or the device under test terminal plus two mounting holes, will be placed on the top edge, here. And we have two measuring BNCs. Plus we have a terminal with external power supply as well connected here. Here is the input, and the power supply will be used for supplying the power input. So this will be used. This will be placed here, like this. This, okay. Yeah, this is the terminal, correct terminal positions. And we have the BNCs monitoring the outputs. These two pieces. So these two pieces will be at best on the left side, because my scope is on my left hand side. So the heavy load terminal will be here, and the light load terminal with the light load output monitoring BNC will be here. We have some terminals as well. These terminals will double the BNC, input BNC, and this is for our MOSFETs. So this is the light load block, this is the heavy load block, this is the power supply plus input block. So this is the rough component placement. Okay, I will conclude this stream for now. I will continue probably, not probably, I will continue next week. I don't know if I will have time on my own to work on the component placement in the meantime, because I want this PCB to be manufactured as soon as possible, because the board with the buck converter is waiting for testing and some following work. So yeah, probably I will continue next week. If I find free time to work on the PCB layout, no, I will work on the layout next week. It will wait. It will wait. No, there is no rush. Perfect. So thank you for the comments. Thank you for being here. I will check my numbers for this stream after the stream is over. Yes, I'm pretty satisfied with the schematic. I think it can work pretty good. If not, then I will make some revision. Not a big deal. So, but it looks promising. It's not a big deal. Input stage, gate driver, MOSFET, terminals. This is basically a simple switch. So it must work. If I didn't make any mistake, and I can't see any mistake there. Yeah. Thank you. See you next week. Bye.